All right. So as we move forward here, trying to discuss electricity and electrical current and building up our understanding of how all this works, uh, what I want to talk about today is going to be how basically now that we know kind of how potential energy factors in here, how we represent it, uh, how voltage and potential difference relate to potential energy. I want to focus today on how we can use this to predict how much charge is moving. That's what we call electrical current. And we're going to talk about how we define that and kind of the laws of electrical current. So our main idea today is that, of course, we have different types of charges in a material. And some of the charges are fixed in place. Others are free to move. So for instance, in a metal, you might have something like this kind of cartoon picture here, where you have electrons that are more or less free to move around in the metal in what we would call a conducting material, like a metal rather than an insulating material. And of course, we have some bound electrons that are really close, the inner shell electrons really close to the nucleus that are still bound and unable to move. But what we're really talking about here are the outer shell electrons, which are loosely bound and free to move. And more or less under like equilibrium conditions, the electrons are going to kind of bounce around randomly, move around, and overall the net movement of charge is zero. But if we do something like this, where if we apply an electric field or equivalently potential difference or a voltage across a wire, so here I'm applying an electric field pointing to the left, and that would correspond, that's equivalent to having a higher potential here and a lower potential here on this side. What that would mean is that the electrons bounce around and jump from ion to ion, from open shell to open shell. They're going to bounce around in such a way that on average they move opposite the electric field, or from low voltage to high voltage. And this is what gives us a thing called the net current, or net motion of charge. So of course, overall, like, it's not as clean as in that last kind of cartoon on the bottom of the slide. If we apply an electric field or a voltage across a wire, the electron's going to kind of bounce around, collide with nuclei, and it'll be a little bit random, but not perfectly random. Overall, the net effect is that if there's an electric field applied to a wire or a conducting material, the free electrons are going to bounce around such that overall, the net effect is that they move opposite the electric field. So here you can see this electron kind of bounces, moves up and down, but overall it moves to the right, opposite the electric field. Or equivalently from low potential to high potential, again. So if we had a wire here connecting two charged pieces of metal, the electrons from the negative plate would end up going towards the positive plate, so the wire would have an electric field in it, kind of pointing from positive to negative. So we could think of this wire having an electric field that guides the current from positive to negative plate. Any questions so far? Okay, good. So the one thing that is kind of annoying about when we talk about electrical current is that, unfortunately, the charge convention that was set up, and we have Benjamin Franklin to thank for this, is that the charge that ends up moving in almost all cases is the electron, which is a negative charge. It's not always electrons that move. If you have current in, for instance, ionic liquid, the ions might be positively charged, so they can move as well. But in a lot of situations, it's usually the electrons that move. So this makes things like kind of annoying mathematically, because when we talk about current, it means we have to carry around an extra negative sign for the charge on the electron. And it makes the math kind of annoying. And it's kind of a constant joke among engineers that the first thing anyone would do if they built the time machine was to go back and tell Benjamin Franklin to switch and call the charge he called negative to call it positive. So we could, of course, always fix this, because if we just decided tomorrow to start calling the electron the positive charge, this would all be fixed. But we're not going to do that, because we kind of have a convention, we're stuck with it. So what we do when we talk about current in physics or in engineering is that really, even though we know the negative charges are moving, instead, what we're going to do is pretend the positive charges are always moving. The net effect is the same, but it makes the math just slightly easier, where we're not going to have to carry around an extra negative sign in every single equation. So if we just pretend the positive charges are moving, the net motion of total charge is the same. But the math gets a little bit easier. So this is what we call, we have kind of two terms here. The real current in like a copper wire where the electrons are moving, we'll call that the electron current. When we think about this mathematically and we pretend the positive charges are moving, that's what engineers and physicists call conventional current. So in circuit problems or problems involving electrical current that we're going to do for the next few days, often you're going to see things like current moving from positive to negative and pretending the positive charge is moving. It's just kind of a game we play to make math easier, where we all know deep down that really it's the electrons that are probably doing the moving. So is that clear to everyone? Any questions on that? Okay, so how do we define current? So really, current is a rate. It's similar to a velocity. However, we're not, when we talk about actual electrical current flowing, we're not considering how many meters per second the electrons or the moving charges move. We also don't care how many particles are actually moving. What we care about is the total amount of charge that's moving. That is, how many coulombs move past a point per second. So it's not number of electrons or number of ions per second, it's number of coulombs per second. Mathematically, current is given the symbol I, because we've already used C for coulomb. So current, electrical current is I. And it's the amount of charge moving past a given point per time. The SI unit for current is called the ampere, or the amp per short, and that's an abbreviation for a coulomb per second. So the way you would kind of theoretically measure a current is we could like kind of pick a point in this wire to watch. So here we have like kind of a beginning of a copper wire, the other end of a copper wire here, and we're going to pretend it's the positive charge is moving, so they move along with the electric field. And if we take a kind of look at a particular slice of this wire, so I can mark this with a pen. So we're going to look at a slice of the wire right here and start a stopwatch and measure for 1 second how many of these, how much coulombs, how much charge moves past this point. If we then take that ratio, that will give us the current, which is represented here as I. So if we pretend the positive charges move, the current moves in the same direction as the electric field, or equivalently from the higher voltage or higher potential energy to the lower potential energy. So for instance, if we watched here for 2 seconds and we saw 10 coulombs pass by this point, we could then say the current would be 10 coulombs in 2 seconds, or 5 coulombs per second, or 5 amps. Give you an idea of what these units mean. So most household household devices, and here I mean kind of like toasters, hair dryers, like kind of what you would call stupid devices, not phones or computers. Typically, you're using currents of around 1 to 10 amps in those things. Something like a cell phone charger, that's giving you like 5 milliamps, so 5 millicoulombs per second. The ion channels we talked about in our cell membranes, those are about 10 to the minus 12 coulombs per second, or 1 picoamp. On the other end of things, we could have a lightning strike. For instance, a lightning strike that kind of takes out electricity or something in an area that kind of overloads the system. That would be something like 30,000 amps, 30,000 coulombs per second, or 30 kiloamps. So that's kind of gives you a range in what these currents mean. So the unit of amp is really coulombs per second. This unit was kind of invented to discuss currents for things like big household appliances. So the kind of normal range numbers all fall for currents for things like stuff you would see in your kitchen or stuff like that. So there's a few, any questions so far? There's 2 laws of current, which I'm going to talk about, and then we'll do some problems. The laws are fairly, I think, fairly intuitive. You should, I think this is a bit more intuitive than the last lecture, for instance. So any questions so far before we do the 2 laws of current? All right, good. So the laws of current are kind of invented by, or were determined by this guy called Gustav Kirchhoff, who was also a chemist. So the first law is conservation of current. This one should hopefully come as no surprise, since electrical charge is conserved. You can't create or destroy charge. The total amount of charge in the universe must be equal. You don't lose charge anywhere. Electrons don't get stuck in corners or junctions. What that means is that if you have like a set of wires like this, the total amount of current going in has to equal the total amount of current going out. And that's called Kirchhoff's junction law. But really, it's just saying that charge is conserved. So here, for instance, whatever I1 is has to be equal to I2 plus I3. So I1 here is the current going in, I2 going out, I3 going out. So if you want to write this law out explicitly, it's add up all the currents going in to some system of wires. That has to equal to all the currents coming out. So here, Kirchhoff's junction law, or conservation of current, would be written like this. So that is the kind of the first law of currents that we're going to need moving forward. Hopefully it's fairly straightforward. This guy also, as you can see, did a lot of stuff. This is only kind of one of the things he's known for. Other interesting fact is that Gustav Kirchhoff is buried in Berlin, only a few meters away. I think he's like next, his gravesite is right next to the Brothers Grimm. which is a kind of cool, interesting, and completely, utterly useless fact that I found on the internet. So you can enjoy that. Tell your friends, impress them. I bet they did not know where Gustav Kirchhoff was buried, but now you do, and you can inform them. Is it clear how bored I am at home that I'm looking up facts like that? Okay. So if there aren't any questions, let's try a few quick problems. These should hopefully, I think, be straightforward. So here we have 5 wires. I know it says 4, but we have 5 wires. What's the unknown current and what's its direction? So work that out, and then when you have an answer, send it to me in the chat. If you have any questions, feel free to send them to me now. So any questions, any thoughts on how to approach this? So here I'll give you the next step. So yes, Jenny, your thought is correct. That's the way you need to think about this. It's not any more complicated than that. If you the goal here is you really just need to add up total current going in and total current going out. Overall, they have to be equal. So if one of them is less than the other, that tells you the direction of the unknown current. So here, for instance, the current going in is less than the current coming out. So that means in that unknown wire, we have to have 1 amp going in. So kind of to draw this here, 7 amps going in, 8 amps coming out. So the 7 going in, that's from the 3 here, and the 4 there. This 8 going out are this 6 and 2. That means there's more coming out than in now, so our unknown current has to be going in, and to make up the difference, it has to be 1 amp. Okay, so this is a standard kind of conservation of current problem, looking at different junctions of wires and trying to figure out what the current, what the unknown current must be. Give me 1 second. We're going to try another one now. So now that everyone's kind of seen how that works, let's try another one. And then not that one just yet. We're going to do. So I got 2 more of these. One should be, I think, pretty straightforward now, and then we'll do the harder one. So let's get the unknown current here. If you're working on this, then, which you all should be, of course, put your answer in the chat so people can compare. That also allows me to know that you're actually working and not just sitting there confused. So if you are sitting there confused, I need to know, otherwise I'll just sit here staring blankly at my computer screen. All right. All right. Well, it looks everyone here seems to agree, which is good. 2 amps to the left. So this one is, again, not that bad. So we have 5 plus 2, 7 going in. And right now here, 9 going out. That means we need more current coming in here. And the difference is 2. So we have 2 amps of current going in on the unknown line. All right, good. This one's a bit trickier, involves some more thought. Here there's, so I'm going to give you guys some time to think about this. So we have, and I don't necessarily expect everyone to get this right. If we get a spread of answers, we could talk about them. But let's think about this for a few minutes and then send what you think is the answer through the chat. So rate these currents in terms of size, A, B, and C. Which one of these choices is most likely the case given the known currents? And also, if you have, feel free to share your thoughts and reasoning with people in the chat. So try to talk about why you think an answer is the case. All right, so from the chat, we have a little bit, there seems to be a consensus, most people picking C, a few people picking E, which are the 2 that I would have narrowed it down to. So if you narrowed it down to those 2, I think that's pretty good. So is anyone interested in explaining their reasoning? If so, say so in the chat, and then it'd be really nice if someone wanted to explain it. That's all I'm going to say. My voice is getting tired. If you don't want to type it out, you could just say, I'll explain, and then you use your microphone. So Owen says current B is the difference between IA and 2. So B definitely has to be less than A. So I agree with that one. And C, if you look at this, yeah, so combining Owen and Brody's explanation here, Owen then looks at, so B has to be less than A, or B has to be less than A, because B is going to be A plus 2, A minus 2. We have all this current going in and then it splits, and B is the difference. So B is definitely less than A from that information. Over here from this other junction, say that B plus 3 has to equal C. So that means C has to be bigger than B. So with that reasoning, you could get that C has to be the answer, which most people pick. So that's good. Brody's reasoning is also a good way to think about it. So what he did is he just picked a number for A and then worked through what B and C needed to be given that number. So that reasoning works because all of the current in the system is coming from this known current and this one unknown current. So if you just pick a number and then work through what these must need to be, you'll get the right relationship. So, all right, it seems like a lot of people kind of got through that problem, got the answer. So there'll be a few on the next homework for this weekend. There'll be a few problems that are like this, conservation of current problems. Any questions before we move on to our second law for currents? Okay. So this law kind of tells us how currents need to break up and add together. Again, just a conservation law. The next law is going to tell us how we can actually predict the amount of current we have given a certain voltage. So for instance, any type of material, as we said, current happens when we apply an electric field, or equivalently a voltage difference or a potential energy difference to some wire or some conducting material. So for instance, this could be done by attaching a wire to opposite ends of a battery or an electrical generator. So more or less experimentally, the current we get is going to be proportional to how much potential energy difference or how much voltage difference our battery gives us. The stronger the battery, the more current we get. Essentially, the battery tells us the steepness of the hill. The bigger delta V is, the steeper the hill, the faster the charge is going to move and the more current we get. So current is proportional to the voltage we apply to a material. It's also going to be inversely proportional to how good of a conductor the material is. This is a property of a wire material we call the resistance. So the more resistive a material is, that means it's going to hinder current. We call this property resistance. We use the symbol R, capital R. And current is inversely proportional to this property. Combining these two statements gives us our second experimental law for currents, and this is called Ohm's law, named after this guy, Georg Ohm. And it's that the current is proportional to voltage and inversely proportional to a material's resistance, R. Basically, it says that if you graph current versus voltage like this, the graph should be linear, and the inverse of the slope will give you the resistance of the material. So a fairly straightforward equation for today. The unit for resistance is volts per amp, which is named in honor of Professor Ohm here as the ohm. The symbol for this unit is the Greek capital letter omega. So the higher the resistance, the bigger the number, this number is. Of course, fundamentally, this law, Ohm's law, is it's really an approximation. At some point, if you apply enough voltage to a material and you start drawing enough current, pushing enough current through that material, it's going to heat up, eventually melt or burn. Or in some cases, the material might not melt or burn or fall apart, but it might start breaking this linear trend. And it might become exponential or start leveling off. So this is really an approximation, but it's a fairly good one. So if we know the voltage on a material, and that's usually given by some power source like a battery, and we know the resistance of our wire or material, we can find the current, the amount of current we have. So the only unanswered question here is, how do we find a material's resistance? What does that depend on? So it's going to depend on as you can imagine, the material itself, but also its overall shape. For instance here, I'm just going to put the equation up first. The resistance is, we'll see, depends on how long our wire is and also how wide and how thick it is. So here, for instance, A is the cross-sectional area of the wire. So using my pen here, that's the area of like the side of the wire. So for this picture of the wire here, A is this circular area. It's basically a measure of how thick the wire is. That's in the denominator. So the wider the object or the wire, essentially the less resistive it is. The more narrow or thin a wire is, the higher its resistance. And generally that's because if you have a thinner wire or thinner object, there's more collisions between the moving charges and the fixed nuclei in the material. So the thinner an object is, the more of those collisions you get in a small space and the more energy is lost to heat. So the smaller or thinner a wire is, that makes the total resistance of the wire bigger. The other effect we see here is that in the numerator, we have the length of our wire. So the longer our wire or our current carrying object is, the more resistance we get. And I think that also, that kind of intuitively makes sense. The longer our object is, the more distance the charges have to move, the more chance it is that they're going to hit more nuclei, lose more energy, going to overall be slowed down more. So this quantity here, the length of our wire, increases the resistance. This last number here, the Greek letter rho, this is an experimental quantity material property. It measures just how intrinsically conductive or resistive a material is. We call this in physics, this quantity, the material resistivity. And it just depends on really what your wire is made out of. So it's, again, a material constant. Kind of some values here. See, materials that are known to be really good electrical conductors, like copper, for instance. 1 second, Owen, I do see your question. So copper here has a really low value of this resistivity number. That's because it's a really good conductor. Generally, metals have really low resistivity, copper being the lowest. As you get up into things that are kind of, they still conduct, but they're not the greatest conductors, you'll see the resistivity number increases. So water with salt in it is conductive, but not as conductive as copper. I guess like pure water has a much higher resistivity. So if you know pure water is not as good of a conductor as seawater, and we see that here in the resistivity increasing. What's going to be important for us later, though not today, is of course the overall resistivity of a bilipid layer or cell membrane. We'll see that that's intrinsically very high, which plays a role into how nerve conduction works. Though we're not going to talk about that today. So Owen, as for your question, that so for long wires, does current get amplified? So for instance here, I think what you're probably referring to are transmission lines. So like the power lines that kind of go between cities. So for a really, really long power line, if you're trying to, like, for instance, deliver electricity from the power plant to your house, wherever it is, you have to have an electrical current that travels really far. And what that means is it's going through a really long wire. And in particular, that does, as you say, increase the resistance, and it limits the actual voltage that you get at your house. So as we'll see, the increasing of the resistivity means we need to really generate a really high voltage at the power plant to actually get the current to go really far away. So yes, this is a problem. So in transmission lines, if you're like sending signals really far or just trying to transmit power, you do have to kind of amplify that signal or boost it along the way. Another thing that this plays into is this is the reason we use what we call alternating current rather than just direct current. So if you notice, like for power plants or household electricity, you may have heard that we don't really use just direct, the current just doesn't go directly from the power plant to our house in one direction. Instead, it oscillates back and forth. The power plant causes this whole oscillating current through the wires. And the reason is that that means any one charge doesn't have to move very far. It just oscillates back and forth, and that limits the amount of resistive losses we get. And this is one of the reasons why we use alternating electrical current for power transfer rather than direct current. So that's a very good question. I hope, at least I think, that's what your question was. And then another question from Brody. So what causes the material's intrinsic resistivity to increase? So like, for instance, why is tungsten less resistive at a lower temperature? So that's a really good question. So it depends, one, on basically your intuition is kind of correct. It depends on the amount of collisions the electrons experience. So as we have as a material heats up, essentially, you have just more random vibration and motion of the electrons kind of in any direction. So at colder temperatures, it's much more likely, or it's a better approximation that the electrons are kind of just moving in one direction with our electric field. At higher temperatures, they do tend to bounce around more randomly, just because that's kind of what temperature is. It's this random microscopic motion of the free charges or the free particles in a material. So at higher temperatures, you have much more of this random motion, which ends up leading to more collisions. That's kind of the simpler cartoon picture, the way to think about it. So that's why at lower temperatures, tungsten is a bit more conductive than at high temperatures. Right. Thanks, guys. Both of those are very good questions. So moving, as we want to compute the amount of current we have based on the material we have, if we know a material's resistivity, and these are here, this is the table, this table on the left here is the table from the text, it's in chapter 22. If we know this resistivity and we know the shape of our wire, we can get the resistance. And then if we know the voltage difference we put on the wire, we could use that to calculate the current. So I'd like to finish today's class just with a problem like that. So let's actually let's go back to this tungsten. So Brody's question kind of led into this next problem I have for you guys. So I'm going to give you, here I give you some, for instance, ideas of some numbers for a light bulb. So here we're going to just kind of pretend that household electrical current is just normal, straight current. So household voltage, if we plug in a lamp into an outlet, that gives us 120 volt difference from one end of the wire through the light bulb to the other. And on average, light bulbs, a standard 100-watt light bulb, you don't really need the 100-watt number here, but you do need to know the current going through that. So here, this is a 0.83. The wire has 0.83 amps of current. And we have a 120 volt power source, so 120 volt potential energy source pushing that current. From this information, what is the resistance? So this first part A here, Part A is asking you to find this number, the resistance. Part B is then asking you to find, if we're given the diameter of the wire, you can assume it's a cylindrical wire, so it has a circular cross section. So that diameter will allow you to measure the area. Then from this information, so you can find resistance in part A, and then use that with the information given to find how long the filament in the light bulb must be. So the reason tungsten is in this list is because those, in like an old school incandescent light bulb, those filaments are made of tungsten. You'll need to pick a resistivity value for the light bulb. I would suggest picking the hotter one because that light bulb is going to heat up. So any questions on kind of how to work through this problem? Otherwise, I will just, I'll be quiet for a bit and let you guys compute and then check in about 2 minutes. But if anyone's confused, please ask now, and I will, I can try to talk through things again. All right, any questions along the way, just feel free to send them. Otherwise, I'll be quiet for a bit and let you guys work. Okay, we have a few answers here. So about 3 people getting the length of the wire to be about 28 centimeters. So it does seem a bit like long for the inside of a light bulb, but the wire is kind of coiled. So we don't know how big of a light bulb it is. It's kind of wrapped around itself a bit. It's possible that I made a, that this should either be a smaller current or the diameter I made a bit too small. So the diameter is probably bigger than 35 microns. So that's probably why, if you're getting a little bit of a bigger answer than you expect, that is probably why. But if you're getting 27.8 centimeters for this number, for these numbers, then you're working through the problem correctly. So let me, just to kind of summarize, so if we want to find, let me clear these arrows a bit. That's not letting me reset the slide. Oh, there we go. All right, so if we want to get the resistance here is going to be delta V divided by I, which is equal to about 100 in 145 ohms all around. Once we get that, this equation will allow us to get the length. So take this number, put it in here for R. So we have R times the cross-sectional area of the wire divided by the material's resistivity will give us the length. And that comes out to be around 27, 28 centimeters. So does anyone have any questions on that, going through that problem? Again, the answer is a little bit bigger than we would expect, but I think that's because I made this diameter a bit too small when I put together the problem. All right. If not, then the set of problems I have for you this weekend, there's going to be 5 problems. They're all conservation of current and Ohm's law problems. So these two should be, they're all kind of along the lines of the problems we did today. So if you don't have any more questions, we'll kind of finish here for the week, and I'll see you guys on Monday. One last comment is just that a lot of things, resistors are devices that are kind of used for controlling current in devices, or also taking electrical energy and converting to heat energy. So you might hear these things called resistors. They're devices that are designed to have a particular resistance. They're usually made out of tungsten or other materials if you need something that's higher resistance. But a good example of these things are like the heating elements inside of a toaster. They're wires that are meant to have a slightly higher resistance to convert electrical energy to thermal energy. So on Monday, we'll talk about kind of how current carries power and things. So if there aren't any more questions, you can feel free to leave. Have a great weekend, and I'll talk to you on Monday.